So there are two things I want to do in this segment. So the first thing I want to do is I want to convince you that these simple models that we're building, right? We're modeling with matrices and vectors. These simple models that we build where we can write down a transition matrix A for the state of some system can get really, really big, really, really fast, and they can actually be quite sophisticated and explain lots of interesting real-world phenomenon. Okay, that's the first thing I want to do. Then I want to give you some examples of how the system could break down and some of the weird things that could happen if you're not careful about how you construct the system. Okay, so you'll recall in the last segment we built this very, very small model where we're describing the weather tomorrow in terms of the weather today. So you can have a state x, and essentially the elements of this vector x are the probability that it's rainy, the probability that it's nice, or the probability that it's cloudy in Seattle. And we can essentially get the probabilities tomorrow given the probabilities today using the transition probabilities for all of these states. You can write them down in a matrix. Now, what's interesting, the system can get really much more complicated, much more interesting very quickly if you just consider adding more features. Okay, so first, let's look at planet Earth. What's interesting about this model is if I really wanted to do a serious model of the weather, that I would say, if I'm modeling the weather in one little grid box on Earth, I know that it actually depends, or at least probably, on what its neighbors are doing. So very quickly, I could actually have this rainy, nice, cloudy description, but for hundreds of thousands or millions of boxes on the surface of the Earth. Okay, one for every position, maybe every square kilometer on Earth would get its own rainy, nice, cloudy probability, and I would stack those into a gigantic vector, right? It's 3 times a million, maybe tall. And I would have a really big transition matrix that tells me, given all of these combinations of rainy, nice, cloudy at all of the locations, what's the probability of it being rainy, nice, or cloudy tomorrow at all of those locations? Okay, so this could get really, really big, really, really fast if you start describing this on a, on an actual domain, like even if you just did the Puget Sound or the Gulf of Mexico, these would still be extremely complicated systems with thousands, if not millions, of states describing what it's like today. You could also imagine having additional features. Rainy, nice, cloudy is a very crude approximation. You could imagine having temperature, humidity, precipitation. You could imagine having what is the sun activity that day, what's the season, and you could have many more features for every grid box. Okay, so that's another way to make this thing richer or more interesting. Another interesting, so this was weather model. Let's now consider that this is, instead of being a weather model, this is a disease model. Okay, so you can either think of this as the flu or zombie virus, whichever you're more interested in. So I could be sick, I could be healthy, or I could be in recovery from a sickness. All the numbers would change. I'm not going to redraw them. And then you have the probability of being sick today, healthy today, and in recovery today. And given those probabilities today, there's some transition, there's some probability of what state you'll be in tomorrow. Okay? Now there are geospatial dynamics to disease. This is very interesting and very complicated. But even if you don't take into account the distribution of people on planet Earth, another way that this system could get big is just by considering more people. Okay? So for example, I have my current flu state. Currently, I'm healthy. But there are billions of people in the world, and each of them has these 3 numbers. So maybe I have, 18 or 20 billion numbers in a big tall vector describing the sick, healthy recovery state of every human on planet Earth. Okay? And my probability of being sick tomorrow is not just dependent on me. It's dependent on if the person in the office next door is sick, or if my kid is sick, or if his daycare mates are sick, then in 2 days maybe I'll get sick. Okay, so this is an extremely complicated system with billions and billions of factors describing it that are all relevant to driving a prediction of what happens tomorrow. What's interesting about this disease model and also in the weather model is although there are billions of people or millions of spatial locations in the weather example, the ones that directly matter to me on a day-to-day basis, there might only be 1,000 people I come in contact with on a daily basis, or 10,000. Everyone on my bus route, the people in the cafeteria, my family, my friends, right? I have some list of people that I come directly in contact with, and those connections are the ones that could make me sick today or tomorrow, okay? So this transition matrix, this big A matrix that tells me, how I'm doing today, how everyone's doing today, and how everyone's going to do tomorrow, is going to end up being pretty sparse. It's going to have mostly zeros, because if I'm right here, then I'm not connected to the 6 or 7 billion people, right? I'm only connected to a few thousand people with a ton of zeros, in the middle. So this is going to be mostly full of zeros, and you can have essentially some network describing how all of these people are connected, and you can get very rich, very interesting dynamics. Okay. So that's how systems can get really, really, really big and interesting really fast. This is just, kind of an analogy for how these things would work, but it's actually not too far off from how you would actually build a model, interestingly enough. Okay, great. Okay, so the next thing I want to show you now is the following. Last time we looked at this probability model for the weather, and we had this A matrix that we constructed. We constructed this A matrix essentially using these numbers for, if you're rainy, nice, and cloudy today, what are the weather probabilities tomorrow? And if we run this, we see that very quickly the weather converges to a state of steady state distribution where it's 40% chance rainy tomorrow, 20% chance nice, not tomorrow, like in 10 or 20 or 30 days in the future. This is the steady state distribution. So after some point in time, I can't really tell the difference. I just get some mixture, and some 30 days in the future, all I can tell is that it's a 40% chance of being rainy, 20% chance of being nice, and a 40% chance of being cloudy. Okay, I don't get any more information than that. Even if I knew exactly what the weather was like today, I'm still going to get this kind of steady state distribution. But that's fine. All of these probabilities add up to 1 because something's going to happen. It's either going to be rainy, nice, or cloudy. But weird things can happen. So for example, I told you that my probability matrix A, all of the columns, every element in each column has to add up to 1. That's the probabilities all add up to 1. Remember, this is rainy, nice, and cloudy. So what if I accidentally made a mistake and I added these numbers up wrong, and I said, well, if it's rainy today, maybe I think it's a 90% chance of being rainy tomorrow, and I don't change any of the other numbers. So this is a huge logical problem, right? We know that it can't be 90% chance of rain tomorrow and 25% chance of nice and 25% chance of cloudy, right? That adds up to more than 1, and you can't have more than 100% probability of something. So this is what happens. This is what can go wrong. And oh, how wrong it can go. Okay, what can go wrong? So if my probabilities don't add up to 1, so probabilities might not add up to 1. this is just a mistake on my part. Maybe I built my model and I wasn't really careful and I didn't make all of my probabilities add up to 1. So now I'm going to run this and I'm going to pause a half a second through every iteration and you're going to see what happens. It looks really weird. Okay, so probability on day 7, day 8, day 9, day 10, etc. Notice that my probabilities have rapidly grown larger than 1 and they're just blowing up and getting bigger and bigger and bigger. So this model is going unstable. Eventually this will blow up to infinity, which is completely unphysical. We know this can't happen. We know that there's not a 9,000% chance of it being rainy tomorrow. Okay, it's impossible. So that's one problem. If my probabilities don't add up to 1, and especially if they're larger than 1, remember this first column here adds up to larger than 1, and so that makes my numbers all blow up to infinity. But what if I make a mistake in the other direction? So instead of it adding up to something larger than 1, what if I just forgot to enter that number altogether? So this first column of probabilities adds up to 50%. There's, just a 50% of my state is missing. Now when I run it, notice that my state is actually getting smaller and smaller and smaller. And so this bad broken model is predicting that the probability of weather tomorrow is 0. There is no weather tomorrow. That's terrible. Yeah, all the probabilities are going to 0. Now, of course, this isn't real, but this just tells you why when you build one of these probability models, you need your columns to all add up to 1. This is physically extremely important to have all your columns add up to 1, or else your model is essentially garbage. Okay, at least for a Markov probability model. And we'll get into why these matrices, these systems blow up to infinity sometimes or converge to 0 and other times by looking at eigenvalues and eigenvectors. Okay, thank you.